Probably, well, I would say definitely the most frequent in industry. Simple, rugged, low priced, and easy to maintain. Why on earth would we do anything else? They run at essentially constant speed in normal loads. Speed control is relatively simple using modern inverter drives. Consists of two main parts: a stator, which by its name stays still, and a rotor, which by its name turns. The rest is bearings and casing and so on. Yeah. So, over the page, going to look at the squirrel cage rotor principle. I'm going to consider the squirrel cage rotor as though I stretch like a ladder initially. Okay, it's made of a conductor material. In our case, we'll say it's made of aluminium. Okay, but it's like two ladder styles, the rungs going in between. Series of conductors of length L are short-circuited by two bars A and B. So these are the two bars A and B. These are the conductors short-circuited. Alright. If we take a permanent magnet, move rapidly over the bars at speed v velocity, so that magnetic field B sweeps across the conductors. If we do that, a voltage E is induced in each conductor while it's being cut by the flux, and that's given by E is equal to B times L times V, where B is flux density, that's the number of field lines there is in the magnetic field, L is the length of the conductor, that is in the field, is what's important, the length of conductors that's being affected by the field, okay, and V is the velocity of movement. It is really quite important that we think about why it's velocity and not speed, because direction makes a difference. Yeah, that movement needs ideally to be horizontal across that conductors and not up and down or an angle. You're going to get less voltage induced. Yeah, so we talk about a vector quantity velocity because the direction of movement is important. Okay, so that's what happens. So we've got these conducting bars that are of a magnetic material, so they aren't aluminium. Right, and you move the field across, and we induce a voltage in the bars. All right. So the induced voltage immediately produces a current I, which flows down the conductor under the pole face, through the end bars, and back through the other conductors. So we get an overall current in here. I'll do it in a different colour. In here, of I, and I over 2 flowing in these bars that's going round and round. Alright? No, it's because half of that current in this bar is going to go that way, because we've got well, yeah, but when that's coming out, when the magnet's right over there, there'll be I flowing through that bar, and I over 2 through these 2 bars. Yeah, because if you make the assumption that the resistive path around there, that way, is equal to the resistive path around that way, then if you've got I flowing in there, you're going to get half of it go that way and half of it go that way. By whose law, Lewis? Kirchhoff's current law, yeah? Because if that's 10 ohms and that's 10 ohms, that direction, you're going to get half the current go each way. Remember I said all that theory follows right through, even when you get to stuff that seems really difficult. Them laws are still applicable. Yeah? Okay? All happy with that so far? Right. So, because the current carrying the conductor lies in the magnetic field of the permanent magnet, it experiences a mechanical force. It's called the Lorentz force. So if we pull this magnet across here, the current's flowing around there, and you get a force on these conductors in that direction as you're pulling the magnet from left to right. Force always acts in a direction to drag the conductor along with the magnetic field. Yeah, so these conductors, if you think of a motor, they're free to move. So as we pull that magnet across there, we induce this field, we get a magnetic attraction, and the bars follow the magnet. So in this case, if free to move, the conductor bars would follow the magnetic field to the right. Yeah? Okay? Now, that's reasonably simple up to there, okay? And then some people get stuck when we go on to the next bit. So, however, as the ladder of conductors picks up speed, so we've got a certain velocity, v, 10. No worry about the units that this is moving at. Initially, the bars are stationary, so the difference in speed between them is high. Okay, but as the bars pick up speed following it, the difference in speed, because remember that's the change in magnetic field that causes the induction, so it's the difference in speed that means there's induction. If they ever go at the same speed, that's stop. That's what we're saying. Yeah. So as the ladder conductors picks up speed, the field cuts the conductors less rapidly, so the induced voltage and hence the current decreases. That's because of the difference between the speed of this and the speed of the magnet is reducing as the ladder speeds up. Consequently, if the induction decreases, the force will decrease. If the ladder will move at the same speed as the magnetic field, the induced voltage and the current in the bars would fall to zero, meaning there'd be no force, and effectively the motion would stop. Yeah, we've got to come on to that in a minute, because we'll initially consider locked rotor. So we'll start to think about it going round in a circle in a minute. All right? Yeah? Yeah. Yeah. At the moment, we're considering a permanent magnet, but we don't pull permanent magnets around the outside of a motor. So that's all to come in a minute. All right? Yeah. But it's the relative difference between the speed of the two things that causes the induction. So there's no difference between the speed of the ladder and the magnet. There'll be no force, and effectively it would work towards stop it. Yeah. We know that's coming. That's coming. Slip's coming. Slip always confused me a little bit until I found these notes. So these were quite a good find for me. I thought they were really good. I mean, I picked them out of something else. So this squirrel cage rotor principle, that's what the squirrel cage rotor looks like. And then it'll have all its iron core around that. Yeah. So in an induction motor, the ladder is a closed loop upon itself to form a squirrel cage, as shown above. In a real motor, the moving permanent magnet is replaced by a rotating field. rotating field that's produced by three-phase currents that flow in the stator windings. This we will now explain. Okay, so we don't have permanent magnets. We have, consider a rotor with what's called salient poles, each with a coil of 5 turns. They are opposed, diametrically opposed. So we've got north and south 3 times around the 360 degrees. So north-south, 120 degrees at a phase with each other. So we get 3 identical sets of windings, IN, BN, and CN, 120 degrees at a phase with each other. Yeah. So we got 120 degrees between A and C, 120 degrees between C and B, and 120 degrees between A and B. You're going to come across the 120 degrees quite a lot of times on this module. All right? All happy with that, yeah? Now, the 3-phase supply create what's called a rotating magnetic field, because we connect, and I make no apologies for going back to the old colours, red, yellow and blue, just because they're easier to handle on the board with the colours and easier to see and easier to distinguish than brown, black and blue, right? So what we've got, if you think of each of these 3 colours are connected to each of those windings A, B and C, then the peak magnetic field on A, and then that falls away and a peak magnetic field comes on B, and then that falls away and a peak magnetic field on C, and so on. So if you can imagine this peak of field as going around that rotor, like so, and that's what pulls this squirrel cage round. Yeah, you get a weird, you wouldn't get a constant torque if they weren't, if one was 80 and the other one was whatever the remainder of, you get a lumpy movement. Yeah, but because they are evenly spaced, then the only sensible thing is to space them evenly. Then we're going to come on to having more than 3 pairs of poles in a little while, because that's about different base speeds. But you'd always put them evenly round the. Well, if you drop a phase, then strange things are going to happen. Yeah, yeah. They'll quite often keep going, but they'll get hot. All right. If they're already moving, it just depends on the load conditions and so on. Right? Because what happens is you get the flux pattern where at this position we've got a north and south pole there and the rotor's being held there. Then this pole comes on highest, so we pulled our rotor around to the next position. 3rd position, 4th position. Yeah. See what's going on, can't you? Don't need to dwell on it too long. And then the 5th position and the 6th position, and then we go back to the start. So it's creating a field that's got its peak that's going round and round and round. North pole, south pole are always opposite each other. Yeah? Everyone happy with that? Right. Synchronous speed of induction motors. Because it's the rotating field that turns the squirrel cage in an induction motor, and that's created by the 3 sinusoidal currents at a particular frequency, the speed that the rotor rotates will hence be directly proportional to the frequency of the supply. So 50 Hertz supply will give you a different synchronous speed to a 60 Hertz supply, and so on. It's also possible to increase the number of pole pairs around the stator. This has the effect of reducing the angle between each pole and hence directly affecting the synchronous speed of the motor. So if we put another set of poles between the original set so that we got 4 pole 2 pairs, we'll half the synchronous speed of the motor, because it's only going to go the same distance, half the distance, in the time jumping from the red to the yellow phase. Because they're going to go red, yellow, blue, red, yellow, blue, red, yellow, blue. So the step size is going to be smaller, if you like to think of it like that. Alright? And if you look at the stepper motor, you'll start looking at even smaller micro steps of tiny little angles. Alright? They are completely different, but in that sense, they're similar. Alright? You'll never see an induction motor look like it's running in steps, but that's effectively what it's doing. Alright? Oh, okay, yeah. So, on the next page, synchronous speed. The synchronous speed of an induction motor can be calculated from ns is equal to 60f over p. That's where ns is the synchronous speed in revolutions per minute, f is the frequency in hertz, and p is the number of poles pairs for each phase. Okay, so for a 1 pole 2 pair, you get a synchronous speed of 50 times 60 over 1, which is 3000 RPM. If you double the number of poles, you get 1500 RPM. Alright? That 60 in the formula is just conversion from minutes to seconds. Because frequency is in cycles per second, and then we want the speed in RPM. Alright? So, calculating what the synchronous speed is relatively easy. Now we're coming on to Ravi's favourite subject, slip. Yeah, in general terms, if you slow something down, that's going to have, yeah, yes, yeah. All right. But that's a kind of a bit of a generalisation, because I'd be surprised if it doubled the torque. Yeah, that's just, that just depends on so many other things, and the speed it's running at, because they might say that's constant torque, but it ain't quite constant torque. You'll see in a minute. All right. So, slip. As discussed previously, the field in the rotor is created by the voltage induced in the rotor bars, and it's created by the change in rotating magnetic field. So that magnetic field has gone round at the same speed all day long, frequencies 50 Hertz and so on. Yeah. If the rotor was to turn at synchronous speed, the rotating field would no longer be cutting the rotating bars. There'd be no relative difference between the speed of the field and the speed of the bars. No voltage would be induced to create the rotor field, and hence the torque would be 0. So if the rotor was ever to travel at the same rotational speed as the magnetic field, the torque would be 0. Yeah. For these reasons, the induction motor never turns at synchronous speed. It is always a little behind. The difference between synchronous speed n, s, and rotor speed nr is called the slip speed, or just slip. The slip speed being ns minus nr. Often, more often expressed as a ratio called the fractional slip. okay, or as a percentage slip, and there are formulas there to calculate it. Okay. So the squirrel cage rotor never, ever runs at synchronous speed. Well, the amount of slip you get, as you're now going to see in a minute, depends on how much load you're putting on it. Yep. So, if we look at the start characteristics of a three-phase induction motor. Right. First, consider the situation where we lock the rotor. So we bolt the rotor up so it can't move. Yeah. If you then power that motor up, the relative difference between the stator field and the rotor speed will be at the highest it could ever be. Yeah. The rotor bar generated EMF, and hence the rotor current will be very high, several hundred amps typically. Not something you really want to look at doing. Certainly not on a big motor, right? Because you're think about it as you're sticking all that voltage onto a very low resistance winding, and you're going to create very little back EMF from the thing turning or anything like that. You're going to get a really high current. The force and hence the torque exerted on the rotor will be very high. So you've got maximum force, maximum torque, locked rotor torque, right? When you release that rotor, so you've got this brake on it, you let it go. The rotor will rapidly accelerate in the direction of the rotating field. The relative speed difference between the stator field and the rotor field is reduced progressively. The motor will accelerate until the torque being produced is equal to the braking torque due to the loads applied and the frictional forces apparent. So you've got frictional forces of the motor, and you've got the load that you're trying to move. That constitutes an amount of torque in the other direction. So it'll speed up until those two match, and it'll run at that speed. Yeah. So can you see what I mean about what you get out of it depends on what speed it run at, what the slip is, depends on how much load you've got on it. Yeah, I don't know for sure. I'm not an expert, but I would imagine they'd quote it at a particular typical value. They might even quote it at maximum load. I'm not sure, but they will tell you. I'll give you a slip value, but it might well be at or around or a certain percentage of maximum load, because it is load dependent. Yeah, it's not going to vary a great deal between a lower load and maximum load, but it is going to vary. Yeah. Yes, we're going to look at that in a minute. Yeah. Yeah, it's not a massive amount. It's not a massive amount. So thinking of it like that, if we have no load, all right, you can't have absolutely no load because the rotor's a load and the bearings are going to put load. At no load, the percentage slip is small, usually less than 0.1% of synchronous speed, so it's not very much at all. Yeah? Consider a motor running initially at no load speed. When you apply a load to the shaft, the motor will begin to slow down. Yeah? So that's found this equilibrium where you've got a slight amount of slip according to the frictional load. Right. You then release the brake on the car, whatever it is you're trying to move, and you put a load on it. Yeah. Motor will begin to slow down. The effect will be to increase the difference between the rotor bar speed and the rotating magnetic field. So that the relative difference between the two will increase. This in turn will increase the rotor bar current progressively. In turn, that will increase the motor torque. Yeah. The motor will not slow to a halt. The motor torque and braking torque from the load will reach a state of equilibrium, a new state of equilibrium, at which the motor will then turn at a new constant speed. Yeah. So you put this load onto it, motor's initially slowed down, but it'll find its equilibrium and stay at that speed, and it'll have a certain amount of slip. Yeah. Yeah, all we're talking about at the moment is a motor on direct online, so just a start stop. Yeah. Next week we'll consider speed control. So, rotor speed and load. A bit more. Under normal loads, induction motors run very close to synchronous speed. For larger motors, 1,000 kilowatts or more, at full load, the slip rarely exceeds 0.5% of synchronous speed. If you think about 3,000 RPM, right, 10% would be 300, 1% would be 30, so half of that would be 15 RPM slip under full load. Yeah. For small motors, less than 10 kilowatts, at full load, the slip seldom exceeds 5% of synchronous speed. This is why induction motors are considered to be constant speed machines, because they will run at a constant speed for a given load. That'll be different if you load it up more, but for that load, that'll stay constant. Right? However, because they never actually turn at synchronous speed, they're sometimes known as asynchronous motors. All right? You can, but the construction is very different. It's not squirrel cage. You'd have to create a field in the armature, yeah, by getting electricity in there and having brushes. Yeah. So what the difference is, you're not getting this drop away of that magnetism between the rotor because the relative speed, because you're going to keep you're using a constant supply to make that magnetic field in the rotor. So that's then going to follow round at synchronous speed. But you're adding complication then because of the brushes. Yeah. Well, yes, but big motors won't be permanent magnet. No. So it all depends on small motors can be permanent magnet. Yeah. Yeah, but when you get up to bigger motors, they aren't going to be that. They're gonna have a wired armature with brushes, carbon brushes. All right. Either that, or you're going to use induction to induce a field into the rotor. So you could have a brushless design generator. Because if you go to where Roger worked at Sizewell, the field current, so the rotor current is achieved through induction. So the exciter induces an AC voltage without any brushes into the rotor. And then inside the rotor is rectification to turn that into DC to create the permanent, to create the magnet of the rotor of the generator. You need to have that created electrically because you want to be able to change it so you can control the output. Yeah. So to keep you can't vary the output by varying the speed of the generator because then you change the frequency. So the only way you can do it is vary what's called the excitation, which is the current in the rotor. I think the guys who used to be on this course told me there's as much as 1,000 amps DC flowing in that rotor, depending on what the output is. There's some rectifiers in there, that's all I can say. That's not these little 1Ns that you get, 1N 4000s. They're a bit bigger than that. when we got shown through there, once this mechanical guy, he looked at the little oil flow, the oil flowing into the bearing. So he said to me, I always look in there when I come through this turbine. He said, I know what the job's like if that ran out of oil. Yeah. Alright, so asynchronous machines, because they don't run at synchronous speed. I'll leave you to look yourself into what these motors are like, but they usually got brushes. And you can find out what it means by brushless designs as well. Alright. Torque speed characteristics. The motor is dependent on speed, but cannot be expressed by a simple equation. The preferred way to show this relationship is in the form of the curve now. Typical torque speed from a full load torque is capital T. What I'm saying in that diagram there, if you look on the left hand side, locked rotor, you'd expect to get, so zero rotational speed, expect to get 1.5 times the nominal full load torque. Yeah? And then when you let it go, it falls away and it reaches this point called the pull-up torque. So starting torque is 1.5 T. And the maximum torque, called the breakdown torque, up the top there, is typically 2.5 T. Pull-up torque is the minimum torque developed whilst the motor is accelerating from rest to breakdown torque. Alright, T is the nominal torque shown in there, and where that crosses N, which is the synchronous speed, full load speed is N. Alright, so that point there, full load. You can see as if you go beyond the full load, or you hit synchronous speed, then your torque's down to nothing. Alright? So at full load speed, the motor runs at speed N, here. If the mechanical load increases slightly, speed will drop until the motor torque is again equal to the load torque. As soon as these are equal, the motor runs at constant but slightly slower speed. We already talked about that, yeah? If the load torque exceeds 2.5 T breakdown torque, the motor will quickly stop. Small motors, 15 horsepower less, develop breakdown torque at speeds of about 80% of synchronous speed. Big motors, 98% synchronous speed. So it's about the scale of the thing. So there's no kind of hard and fast rule. That's a lot more complicated, and there's so many varieties of machines out there that you just got to look very carefully at what your needs are. Alright? Are there any questions about that? The idea of that is to give you a flavour of the type of information that you may or may not need to look into. Yeah, and you'd pick out of that what was the really important things for your application. Remember that some motors might have advantages that really mean nothing to your application. They don't matter. They might have disadvantages that don't matter to your application. But they have the good things that you're really looking for. That's what you're looking to pick out. Yeah. All right. Any questions?